Okay.
Hello, super. All right.
Okay, so this is day 4 of second SARA Statistics Winter School, and I welcome all of you, especially to our today's instructor, Dr. Cecilia Baldoni, and big and biggest thank you to her for agreeing to taking this session. And right now in Germany is morning 5 around 5:30 a.m. And thank you so much, and we huge love and respect for your dedication and helping us with the statistics. And it's not too late to wishing Happy New Year as well, right? So from all the students and from the team of SARA,
Still
Happy New Year to
January.
you. And uh,
Happy New Year.
I requested for a help to Professor Dr. Cecilia regarding statistics, and she happily agreed to help all of us with the statistics. And this is the second time she is teaching students of SARA. And a quite little background: Professor Cecilia, Dr. Cecilia has done PhD in Germany, and after that postdoctorate also in Germany. And she is a biostatistician, and recently, her personal website got award as well for the creativity and the style of presentation, the information. So we are very excited for today's whole day session. So, right. So over to you, Dr. Cecilia.
Thank you so much for the very kind introduction and Happy New Year to all of you as well. And I'm very happy to be here, and I'm happy to share the day today with my very good friend, Dr. Kavitha, which is here with me today. She will do the session of today lecture. And yeah, but maybe we can start sharing so for
Yeah.
those of you who don't know us, we can present ourselves a bit and then we can start.
Yeah.
Thank you.
Yeah. Do you see my screen?
Yes,
Um,
need to put the
My
slide
mistake. I
share.
completely missed Dr. Kavitha. Hello, Dr. Kavitha. So
Hello, that's
I'm
no
so
problem.
sorry.
That's okay.
So I
That's okay.
completely, I thought it's like one person, one session, but you're doing together. That's fantastic. So Dr.
Yeah, yeah,
Kavitha is also recently completed PhD in Germany, and
yeah,
originally she's from India,
yeah.
and she has studied in Germany for her work. And fantastic. Welcome both of you. And I'm sorry, it's my apologies. I just okay.
That's okay. That's all
Yes,
right.
okay.
That's no problem.
So
Yeah, thank you so much for having me here as well. I'm really excited to yeah, talk about today's lecture and also be part of this. Okay, I hope all of you can see the screen, right?
Yes.
Okay, so I will put it in slideshow mode. And yeah, so like all of you said, we are on day 4 today. And yeah, maybe we just give a little bit of introduction. So yeah, Cecilia can go first.
Yes. So yeah, as Ajay said, I am a postdoctoral research now. I finished my PhD very recently, a year and a half ago. And I studied a bit biology and behavioral ecology. So mostly I was working with animals, which is a bit far away from what some of you are working on, but you will see the foundations of science is the same. And yeah, by the way, these slides we will share at the end of today, and there are some links and some things you can use yourself. And yes, I will pass to Kavita that can present herself.
You. Yeah, I'm Kavitha. I am originally from Bangalore. And then I came to Germany to do my PhD at the University of Constance. And right now I'm also working as a postdoctoral researcher. And my main interest, again, has been on working with animals. So mainly with very small insects like honeybees. That's a picture of me surrounded by bees. And I'm also a behavioral biologist, but also a neurobiologist as well. And very similarly to what Cecilia had said, and very similar to all of you, I've also made use of different kinds of data in my PhD, I mean, I've also analyzed them in different ways. And I guess in many ways, today's lecture would be about that, of how data is so random. Data can be from entirely, completely different studies, like all of you had mentioned, political studies and media studies, to biology, to data science, and how one can look at it in different ways and actually extract information from it and, give to further like information like out of it as well. So I will get started to today's agenda. So I think many of you know that we will be covering these different topics. So mainly on probability distributions and on framing what a hypothesis is, which is the base of any research. Any research needs to have what a question is, what a hypothesis is, how we frame it, and what a what a significance testing is. And then we would move on to different kind of tests, statistical tests that one can do, things like a t-test, an ANOVA, a chi-square test, and so on. So today's lecture, to how we will go through it, is we have the lecture part. So I will do the lecture for today, which would be about 40 to 60 minutes. And it will be followed by a practical session with using R. We know that all of you have been learning to use R the last 3 days. So we will, of course, have some practical session as well with it. And general housekeeping rules, just stop us anytime if you don't understand anything. You can ask any question. You can drop your questions in the chat, because I know that all of you have to be muted right now. So please use the chat feature and the hand raise feature. Both of us will be checking the chat as I'm giving the lecture. Cecilia will be checking the chat as Cecilia will be doing the R programming part. I will be checking the chat. And if you're stuck on a code error, please let us know and we can fix that together. And you could also answer each other's questions as well in the chat. So there is a bit of communication in the chat with us, but also within yourselves in the room. And as far as possible, we would like to make this a very interactive session. So please feel free. Please don't be, shy or anything. We are here to help you. Okay. So with that said, let's move on to the lecture. So that today's, the first one was probability distributions. So before we actually talk about probability distribution, what is a probability? So all of us have seen that there's so many events that can happen all the time. Things in life is quite random most of the time. So for example, you have cursor. Great. So for example, you can have like the weather, like where you can have different chances of rain. What does that mean? Some days you have a high rainfall, 70 to 90%, 20% of rainfall. What does a chance mean? So probability is the chance that an event will happen. So it is the ratio of the number of ways a certain event can occur to the number of possible outcomes. For example, flipping a coin, you have the total is two outcomes. It can be either a head or a tail, right? And when you flip a coin, you have a chance of only one of those things coming up, either a head or either a tail. So chance of it is 1 by 2 or 50%. There's a 50% chance that you will get a head or a 50% chance that you'll get a tail. Similarly, when you play a game of dice with your friends, for example, and you say that you want a total of 6 to win this snake and ladders game, for example. So what is your chance in that? So you have a 1, so there are 6 options in a dice. So you have an option of 1 over the 6 options. And in the second dice, you have another 1 over the 6 options. So your probability of getting that 6 on both of those dice at that point in time in that game is 1 by 36, which if you actually divide and see is a very low chance. Okay. Now, but one probability is often not enough. For example, one of you, like here, who is in this class, Mohit, for example, can flip the coin 10 times as compared to, say, Mr. Kirtivasan, who can also flip the coin another 10 times. And you could have completely different probabilities. Mr. Mohit can get heads, tails, heads, tails, head, tails. And Mr. Kirtivasan can start off with the tails and then go with a head and a tail and a tail and a head. So the distribution can be entirely different. And as you would have seen in your in exams as well, it's not that you can always say that this one class is going to get 50%, everybody's passing on 50%. But no, everybody gets different scores. Some people score 50%, some people are scoring 65 to 70%, some score 80, almost even 99.9%, but very few people also like 20% or 30% marks. And another example is that, say you're surveying in a village, okay, and let's say you are looking at different heights of people. It's always not the case that, not everybody is not at the same height. So people are different. There is the role of gender, there is the role of cultural, but there's so many different things. And genetics and so on. And because of that, some people are 5 feet tall, some people are much taller, 6'5" tall, and some very few people are 4 tall at the height of 4. So when an experiment can have many possible outcomes, we cannot just depend on a single probability. And what we need is a probability distribution. So a probability distribution shows all possible outcomes of a process and also shows how likely each one is. So you can actually calculate the differences of how Mr. Mohit was tossing a flip coin compared to as to Mr. Kirtivasan was tossing a flip coin. So like here, for example, by tossing a flip coin twice, you can actually list out, you can see the distribution of the different kinds of outcomes. Again, like I said with the dice game, the chances of you throwing a 7, the probability is also slightly higher because there's so many different ways in 2 dice that you can have a total of 7 as compared to getting a total of 2 or 12. So there are, it's a different, you can look at all the different options, and that is exactly what a probability distribution is. Is there any questions so far? Good, all good? Okay, I'll move on. So, like I said earlier, these are actually from a study. So if you are looking at any studies that you mentioned this morning, one could also lay out the distribution of the data from your studies, like men's height and women's height, which this is actually from a study from 2020. And you can look at where where people lie with their heights. And similarly, like I mentioned with the grade chart, for example, like you can lay out all the people on who are passing and the minority of that particular class per se would be people who are getting a complete A grade or a complete F grade, passing with a 98 to 99% as compared to passing with a 10 to 20% of marks. So the key distribution here is that probability is just one number, and probability distribution gives you the whole picture. And to talk about the distributions properly, we need to learn another concept. And this concept is called a random variable. So it sounds random, that's true, but that is a number that represents the outcome of an event. So which is quite an important thing, because to say that you're flipping a coin, you need to name it. You need to say that you're looking at the number of heads or the number of tails. When you're doing a die roll, you name it. You need the height of a randomly chosen person. So the probability distribution tells us how likely each value of x is. We have you have either discrete random variables, which is that they are distinct or separate values, that they are countable outcomes. And there are continuous random variables, so which are any value in an interval or a range. Okay, so with the discrete random variables, I mean, you can have examples. For example, you can call your random variable, like I said earlier, the heads or the tails. So it's either one of the two, right? And so that is a distinct or a separate value, and that falls under the discrete random variable. Now, a height, for example, like measuring the heights of different people in a village, for example, is a continuous random variable, mainly because height can start from really low, like maybe 3 feet or 4 feet or whatever, and it can go on to, again, a measured value of, say, 5 feet or so on. And as it lies in an interval or in a continuous range, it is known as a continuous random variable. Now, let's just try to do a little game here, maybe. And maybe one of you, maybe or some of you can answer on the chat. What do you think? So here the guess game is, which is a random variable, which is a discrete random variable, which is a continuous random variable. So for example, in most of my data, I looked at bees that sting or not sting. And my variables were either 0, so I gave a 0 for the bees that did not sting or did not bite, and a 1 for the bees that either stung or that bite. Now, what do you think is this measuring these random variables? Is that a discrete random variable or continuous random variable? You can type your answer in this. Great. Dheeraj Singha, that's great. Yes, it's a discrete random variable. Did everybody understand this so far? You can maybe, okay. Okay, great. Okay. Now, what about the weight of your friend living in your hometown? Now, this weight can, of course, go from 0, where your friend can be 3 kilos if he's a baby, or 63 or 83 kilos if he's an adult. So it can be on any range. I learned that the heaviest person on earth today is 635 kilos. So for now, the range lies to 635 kilos. But your friend can weigh anything between 0 to this 635 kilos. So thus, that's also a continuous random variable. So what about let's say you're looking for a variable where you're measuring time. So the exact winning time of men's 100-meter running race, like in the Olympics, say Usain Bolt, his fastest speed was, I think, 9 seconds or something like that, right? Like 9.12. What do you think the exact winning time of men's 100-meter running races? Is it discrete or is it continuous? I see continuous as an answer. Okay. Okay. Why? Can somebody explain why it is a continuous? Any reason for why it is a continuous reason? Because the exact time can lie anywhere. Um, Not necessarily. The look that I have made the exact word as a bold. So this is a trick question actually. So it's the precise time. So now if you look at the precise time, it can be 9.127356. It can be 9.123468. So it is a discrete value. So the exact winning time. So you're looking at that particular time in frame. So that it's just one value. Yeah, like Cecilia says, you can either think of it as a success or a fail. So it's that success point. So that's the number. So then that is a discrete time. But on the other hand, if you look at the winning time of men's 100-meter race and you round that time off to the nearest decimal. So you have value like 9.567, and then you round it off to 9.5. And then you have another value, say that is 9.83 something something, and then you round it off to 9.8. So these are rounded off, and these rounded off values are indeed continuous variables. Okay, cool. So now you can list each of these probable values. And the first one that we're looking at is listing out the discrete probability distributions. So the first one it's a very common one, and this is called the binomial distribution. For example, you can, like I said, you flip a coin and you have the different distributions, and you can put that into like you can visualize it as a chart. So this is the definition of it. I will read it out. So binomial distribution looks at two parameters, N and P. It is the number of successes in a sequence of N independent experiments, each asking a yes or a no question, and each with its own outcome. So success, that is probability with a P, or a failure, which is usually the probability, that is Q, which is equal to 1 minus P. So this is the general definition of it. And it's again very similar to what we've been discussing, the success and the failure and the n, the number of n number of success or the independent experiments, and what you're actually looking for. Like I said earlier, if you're looking at if you're flipping a coin 4 times and you say your aim is to count the number of heads, yes, you will likely get a higher number of heads on the second throw, or by throwing the coin on the second throw rather than on the fourth throw, for example. Okay. And there are other discrete probability distributions. So we wouldn't get into this entirely. These are just other examples, but this is one way of looking at your data. So there's the geometric distributions, where the number of trials needed to get the first successes in repeated Bernoulli trials. For example, here you are looking for the probability of the first 6 on each roll. So of course that is going to be lower. So each time you need to throw a dice, and then you need to see when is your 6 coming up. And of course, your probability, the chances of it varies, and that would fall into a geometric distribution. And you also have what is called a negative binomial distribution, which is the opposite of a binomial distribution. So your number of successes is fixed, but the number of trials as such is a random variable, which is to say that, for example, in the binomial distribution, you are saying the number is that you're flipping a coin 4 times, that is fixed, and then you're counting the number of heads. So then that gets into a binomial distribution. But in the negative binomial distribution, you're saying that the successes, so which is you're saying that it will always be a heads, and then you throw it whatever number of times, and that is a random variable. Okay, so there are also other distributions called a hypergeometric distribution and a Poisson distribution, which is also well used, but I'm just listing it out here for you today, and we can, I mean, of course, we can read up on it and learn about it in your spare time, and we can also discuss it like either today or tomorrow if you have questions on it, but that also exists. Now, the second thing is the continuous probabilities distribution. So here we care about the ranges. Like I said, you have the different weight. Like for example, you can say that I am looking for a weight that lies in the range between say 63.5 kilos to 87.324 kilos. And the important thing to remember here is that in this range, the probability at any single point is going to be 0. There is a question on the chat.
Are we talking still, sorry, Kunai, are we still talking about the exact time of the race, right? Shouldn't that be a continuous variable, as if it is the exact time of winning the race, it can be anything? Yes, time doesn't jump from one value to the other. Between two times, there are infinite possibilities. Yes. So the question was, sorry, the reasoning behind was because when you say, I think Usain Bolt will win the race at 9.12 seconds. And let's keep it at, or 9.1 second. Let's keep it at that. That becomes success failure situation, because I can either be right that it will win at 9.1, or I can be wrong that it will win at 9.2. So in this scenario, and that's why it's a very good example from Kavitha, because it's a very trick question. It makes you think. It doesn't matter the actual numbers. In this case, it matters the intention. So if I say 9.1, I can either be right or wrong. And then, of course, you're right that in this sense, time is like the most continuous variable existing, because yes, there is infinite numbers, but as we intended, as we meant it in this way, we don't really look at all the possible infinite possibilities between number 9.1 and 9.2. In that sense, it's a success fail, and that re-enters in the binomial distribution. But please, is this clear? Is it something that is still confusing? We can also think of another example, maybe. Yeah.
With the discrete and the continuous. Go back slides.
Does my explanation make a bit more sense, or did it only confuse you more? Let's start from there.
Okay.
Yeah.
That's
I'm
great.
thinking of another example, but I think yours was very good, like in this. Yeah, exactly. Any
Exactly.
option that's not exact is not correct or a fail.
Exactly.
Yeah, right. It's the same with the exams, right? You made the example before that you can have some exam in which the passing rate is 78%. So, for example, I had like a German class that was, okay, you have to reach 78% or higher to pass. And I know it sounds like a continuous variable because it can be from 0% to 100%, and I can lay on any point. But in this case, it's just, again, a Bernoulli or a binomial, because I can either pass the exam if I am 78% or higher, and I can lay in any number there, or I can fail if I am 77.9% or lower.
Okay, hope that is clear. Thank you for the question. Please keep asking us more questions. It's good for us also to know if we are explaining it in a clear way or not. Thanks a lot. Okay. Now back again to continuous probability distributions. So Yes, so we're caring about the ranges, and which lies between two different numbers per se, and these numbers can go up to whatever decimal value as such over here. But if you take a probability at any single point in this like overall distribution, it is always, it has to be equivalent to 0, because it cannot be that, for example, I cannot assume that, one of your weights is today is exactly 80.0. That's usually not the case. Your weight can be, say, 80.0123 or so on, or like the probability of saying that one of us weight is exactly 71.1 to the dot, the probability of saying that is actually very low, because that would become 0 as such. Okay. And the continuous probability distributions are represented by what are called the probability density functions, which describes the shape of the distribution. So the PDF, the probability density function, describes the likelihood of a random variable taking on specific values within a given range. So again, when you visualize it, you get to see a shape of it, and these are usually distributed across the range. And with the shape, you can say if it is symmetric in shape, or if it is skewed, if the data is pushed to one side, if it is peaked, if it is, like all the data is aligned in this peakish manner, and so on. And understanding the shape is really important because it provides information about the behavior and the characteristics of the random variable being studied. So if you have a peak, for example, like everybody's weight is peaking at, say, 70 kilos, and everybody else is on the other side. So then you can say for that, that's usually not the case. But of course, in that, you can say that that particular population, it is lining directly on this one. There are lots of people weighing very close to 70 kilos and lots of people not. But if it is a more of what we call is I will come to this, a bell curve, then it's more distributed. The averages, of course, around a particular area under that curve, but then it's more distributed is the key message. So yeah, the most popular probability density function is the normal or the Gaussian distribution. So it is used to approximate for most real-world phenomena, like this is for height, your weight, your test score, etc. And most of the values are near the central peak, and while values away from the mean taper on the ends, like we saw with the test scores. So most people are likely to score between a 65 to 75% in an exam, while people who are usually failing an exam, or people who are usually getting a 99% in an exam, are usually in the tails. So this is usually called a bell curve, mainly because it's shaped like a bell. This is the standard bell curve. The red one is the standard bell curve. And there are only two main parameters that are used to describe here, which is the mean and the standard deviation. So how much a data point would vary from the mean and from the other data points as well. So a perfect normal distribution, which is the standard bell curve, standard normal distribution, the mean, the median, and the mode will always be the same value. So here you see that the mean is 0. So this red one is a standard deviation, like the standard curve. And yeah, the standard deviation is 1. So you see that it's a very symmetrical curve. And the popularity of the normal distribution is due to what is called a central limit theorem. And this central limit theorem states that the distribution of a sample, of sample means, approximates a normal distribution as the sample size gets larger, regardless of the population's distribution. So, which is to say that, yeah, I mean, the larger, so if your sample size gets larger, if it's 1,000 coin flips, so it's not coin flips, this would be continuous data. So 1,000 people's heights, which I think we will try to play around a bit on R soon. So yeah, we will try to see how the standard a normal curve can vary with different kinds of height and different kinds of data. Okay. We will go a little bit deeper with R code when it comes to this and soon actually. So despite the popularity of the normal distribution for your data, it is always not advisable. There are also other types of distribution. So you have the normal, you have the triangular, you have the uniform distribution, you have the log normal distribution, and so on. So it's of course, most of your data will fall into a normal distribution, but let's always not take it for granted. There are other distributions, and it's always good to not be overconfident when it comes to this. With that said, I will just once again go over these topics that we have covered right now, and then we will jump right into R. So probability is one number. Probability distributions shows us the whole picture. A random variable is a number that represents the outcome of a random event. It can be either discrete or continuous, how we saw with the different examples. And probability distributions, therefore, can either be discrete or continuous. And the most well-known discrete distributions are the binomial and the uniform distributions. And the most well-known continuous distribution is the normal distribution. Well-known. It's not the only distribution, okay? So this is time for maybe a tiny 5-minute break if you want, and then we can start seeing the distributions in R.
Before we take the break, any more question? Please ask now, but also later, whenever you
Yeah,
want.
anytime. Any other questions? Is it clear? I can maybe just go on the previous. Oh no, sorry. The summary just in case. Okay. Can you repeat the zero thing in a continuous probability distribution? Yes, of course. So say you're measuring 10 people, okay? And of course, each person is likely to have different heights and weights. Let's say we look at weights because that was the thing that we looked at. Yeah, so I'll just finish explaining the zero thing. So, of course, there are some people who could weigh exactly 63.5, but what is it exactly 63.5? Like you can say that it is 63.5, but then the number on the scale can also go beyond those decimal numbers. So it can be 63.567, 63.854. It can be anything. You can say, I mean, because it would fall under a discrete value, like how we mentioned earlier with the time, right? Like I can say that it is exactly 63.5. I mean, and these would be then discrete values. But if in the case of a continuous variables, in the case of continuous values, it can be anything at that any point in time. So for you to say that the probability of X person, like person X, is exactly 63, like the exact point of you getting a probability of 63 kilos in that population is very rare. It is equivalent to zero. That's exactly what I'm trying to say. Chichi, do you have another way of explaining this?
I mean, to me it was clear. Just want to see if that's the case. I think it's just like one of these, yeah, like you said, very rare occurrences. Like it's very rare that I am right to the 10th decimal about
Exactly.
Kavitha's height. Like I
Yeah.
know roughly how tall she can be, but it's very incredibly statistically not that
Yeah.
possible,
Yeah.
probable that I can say she is up to 10 decimal this
Yeah.
tall.
Yeah.
And the more precise I want to be, the more the probability goes down. So I can say
Exactly.
she is, well, I don't know in feet, I know in centimeters, she can be 1.68 maybe. And then the
Yeah.
more I add decimal, the probability of me being right goes
Yeah.
down.
Yeah.
And then
Yeah.
at some point reach zeros.
Yeah.
Yeah.
Yeah. I mean, and this is also directly related to how, I mean, the way you're calculating the probability of that particular person at that particular time and so on, right? So like Cecilia said, it is also that by dividing it, like, each time you measure it, of course, you divide it and by whatever that you're measuring. And yeah, the number itself goes lower and lower. So it would be not just zero precisely, but also 0.0001% would be a value, or 0.00001, and so on to the 10th decimal. So that's exactly what we mean. Okay, I hope that was clear. Yes, okay. Cool. So maybe let's do a small break if you need. Drink water, go to the bathrooms, whatever.
Mhm.
And then Cecilia will start sharing screen and we will
Yeah.
jump right in.
Yes. So maybe, yes, I will go to the bathroom 1 minute. If none of you needs a break, what you can do in the meantime is to open your art studio, and I will also share mine so we can go through things together. But I would really like for each and one of you to open your art studio and type with me while we do the exercises, because I think it's gonna be better. And yes. So give me 2 minutes and then open your art studio and then we can start, all right?
And I will stop sharing my screen.
All right, so please, all of you, open R and R Studio, and I would like another thumbs up when you have your R Studio open and ready to type. Very good. Very good. I think that makes most of us. This is probability distribution, right? Yes. Let me organize my million screens 1 second. And I can put you here, guys. Desktop 3. This one. All right. Let me be sure that I shared. Yes. Oops. Yes. Perfect. So, are we ready for a bit of R? I need, before we start, I need to ask you, so I will put the chat on. So most of you started using R during this winter school. And I think I saw from the program in the past days, you did like a bit of base R and ggplot. Not able to see clearly on the screen. Please zoom. All right. Yes, I can maybe. Give me a second. I could. Yes, please tell me so we can zoom in a bit. And we can also code maybe like this. How is it now better? Wait,
Yeah,
is
it's
it better?
better.
Maybe they have a big screen up there. Maybe I can do also this. All right. Let me know if you can't see or if something is unclear.
You can also try command and plus sign. It will increase the complete window size. So that will be
Yeah, that's what I
just try.
tried, but I have a weird, yeah.
If it is Mac, command plus, or otherwise control plus.
Yeah, that's what I tried. But I think, I mean, is now,
I think yeah, it was now it's good, I guess. Is it good?
yeah, it can also be bigger. I mean, I don't
Yeah.
mind if
This one
just
is good.
it has to be good for you guys. Yes.
This one is good. This one is good.
Perfect. All right, so you saw already some base R and some ggplot, and so you learned in the past few days how to write code in R. We will go over things related to the probability distribution today, but if there's something unclear, please stop me because I won't be able to see the chat. So maybe Kavitha, you can tell me if there's something. Yeah.
Sure.
All right.
Yeah.
So if we are ready, we can start. So as usual with R, one of the first things we have to do is to prepare our environment. This is a brand new session. I just opened it now, so R doesn't have anything ready. And you can see, as you can see here, I just opened it up. So the first thing we need to do is to load our libraries. And I think in the past few days, you learned how to do, for example, ggplot. And so you load libraries this way, but today we will use a new library that you probably might have or probably not. So to do that, we can do install packages. It's called tidyverse. This is a library that it's mostly like a combination of different libraries. For example, in the tidyverse, there is inside already ggplot and read, which I think are the libraries you used the past day, and the tidyverse just use them, put them all in one package. So if you don't have it, I do, but I will run it anyway. And you run this and it will take a few minutes, maybe longer, but don't worry about it. We can wait. And it should install this library for you. And to check if it worked, if you start typing it, here it is, the tidyverse. And as you can see, it says the tidyverse is a set of packages that work in harmony because they share common data representation. What does that mean? It's like the way they organize the data to do calculations and statistics is the same in all of these packages together. So they can be shared in the same universe. So I will just click on it and load it. To load, I just Control R, but otherwise you can just also run the line. All right, so any problems so far? Did you guys have we installed it already. Perfect. Sorry, I'm slow with the chat. Super. Then, now that we have our package, we can start simulating data. So now for this kind of distribution, we will do a lot of data simulations. Probably in the past or in the future, since you're all scientists, social scientists, and PhD, everything, you will collect your own data, most likely. But today we will either either make our own data or use existing data set that are as some already precompiled data set that are great for practicing. So we will do that. All right, so the first thing we are gonna do is the discrete uniform distribution. For that, the best example we have is the die. So we can imagine rolling a die of 6 sides. So to roll the die, we can use function that it's called a sample. So if you start typing it, it appears, it is in base R. So when you start typing some functions, R is very useful because it tells you where the functions are from, which package they belong to. So this is in base R. So we didn't even need the tidyverse, but we will need it later for the ggplot. So the function sample wants different things inside. They want an X, so a number. They want a size, and then they want to know this replace false. What does it mean? So X will be the number of events. The size will be how many times, the trial time, how many times do you make this event happening? And replace means, do you want the same occurrence to happen more than once or not? So, for example, in the die situation, we have number from 1 to 6. Do you want that the same number can reappear in different trials, or do you want to exclude it? So, for example, it was what Kavitha said in an earlier example was, we make a trial until we get a 5 and then we stop. That would be a situation in which you need this replaced. But so let's start normally. So we say that like in a classic die, we roll a 6 faces die. The classic one, there are also some with 10 or 4 or whatever. We roll a classic one. The size, we decided before we threw the 1,000 number around a lot, so we throw it 1,000 times. And we want to replace it. So this means that out of the 6 options, they can always come out with the same probability. So we don't remove any of the 6 options. So to do that, we say replace true. So if I run this without assigning any name, so if I control enter, what happens is that I have the output. As you can see, there's 1,000 numbers that go from 1 to 6, right? But of course, this is not saved. So we want to save it, so we call it roles. You will find out today that I'm very bad at naming things. So roll of dice, rolls. So I will run it again. And if I say rolls now, oops, as you can see, the numbers are not quite the same. So for example, here the first digit are in the first trial is 3561. The second trial is 6536. Why? Because it just, every time you run it, it just does it again. So it's very unlikely, again, that you get the same combination of 1,000 number 2 times in a row. It's impossible. Or, well, maybe not, but very improbable. And sometimes you do want the same number because, for example, when you are sharing your code with your friends, it's like, okay, can you do a code review of my code and can you show me, like, see how it works? And then you don't want to have different numbers between things. To have the same numbers every time you roll it, you can call this seed function. You give it a random number. This doesn't matter. Usually people put 1, 2, 3, 4. You can put 9, 8, 7, 6. Doesn't really matter. What this does is that, oops, what is seed? Set seed, sorry. set seed, or I'm so sorry, should have. Set dot seed. Here it is. Yes. So it's set dot seed. What this does is that it fixes the outcome. So now every time I run these roles, it will be always the same combination of numbers. Again, today it's not really necessary, but it's something good to know in the future if you want to like be more replicable in your code and you want to share the code, that it always has the same outcome. All right, so we have our yes. Yeah.
Just a comment. I mean, some of the things that like as Cecilia is saying, you could also have it as a comment with the hashtag next, like
Yeah.
she just explained the set.seed. And in case you want to make a note for it in the future, you could also just use the hashtag and comment right
Yeah.
next to your code, so you remember.
Yes, that's true. Make a comment. Thank you so much. This was a very good point. Yeah, for example, I used one here for the title. So this is just what R ignores. It's just everything that is behind the hashtag. It's like it doesn't exist. So, all right, we have our roles. We can also, for example, here it was quite okay. I could print it and see all these numbers, but sometimes you also just want to see some of the numbers, not all of them. So we can do head. And if you run head of an object like rows, it just gives you the first 6 digits. Entries. But you can also give him, like, I want to see the first 20 points of rows, and then you can tell how many of these values you want to see, and it can be any number. It can be 1,000, but then it's not necessary, but it's possible. Yes. So let's say I want to see 10. All right. Now we want to plot it, right? Like one of the first thing we will see today, we will repeat it a lot. You always want to plot your data to see. Like today, the point of this morning is to see the probability distributions and to see the plot so you can visually associate. But there's a problem. This, like if you see on your right pane, there is in the environment section, you see that this is just a list of numbers. ggplot doesn't like this format. So if I try to plot this with roles as it is now, it will not work. What ggplot likes are data frames or data sets or tables. So the tables with like very nice notation with column and rows, even if it's only one column, one row. But ggplot would like to see that. So we need to make ggplot happy. So what we do now is we call it roles data, just to distinguish the two so we can see it on our right pane. And we ask, there is a function called tibble, and this creates, as you can see here, it creates a data frame. It's in dplyr, which is one of the packages inside the tidyverse. So tidyverse, so far we've seen that it has dplyr. So we didn't need to load the dplyr because it was already inside the tidyverse. So tibble. What do we put in the tibble? We need to put roles, but the problem is that roles comes without any column name, right? So we have to tell that the tibble has a column that we will call outcome, and that column outcome will have the roles data in it. So if I run this, then now you can see that in the environment there is the old roles that were just random samples, and now we have the data frame called roles data, which has one column called outcome. The other thing that I think you guys did in the past few days, but we will just do it quickly, is how to access this specific column. Maybe you know already. So if I want to select, in a case in which I had a data frame with many columns and I want to select only one, I will need to ask for the data frame, roles data, $sign, and then as you can see, the only column possible pops out, and I can say, yes, I want to select this column. And if I enter it, again, I can see all my numbers. But this is the way how to access a single column in a data frame. All right? So we have our roles, die roles. We have our data frame. We can now move to ggplot. ggplot is another library that is within the tidyverse universe. So you don't have to load it. Once you load the tidyverse, you have it as well. So we start ggplot. We need to give it the data frame. In this case, it's roles data. We need to set the aesthetic, like the X and Y axis. In this case, we only have one column, so it's quite handy because we can just say X. And now, so when we created this data frame, R is a very smart machine. So it saw a bunch of numbers in like integers numbers, and it decided that this column was full of integers. So as you can see here, it just defined that this column is for integers. But in this case, we would like to change this variable into factors. I don't want to do it in the data frame because maybe I still like the integer form because, you know, you can always do math and you can do calculations. But for the ggplot, I would prefer to change them into a factor. Why? Because a factor, it just groups all of the options into 6 different categories, from 1 to 6. That's the maximum categories I have in my data frame. So if I don't want to change the data frame on its own, I can ask ggplot to treat these variables as factors. And to do that, I just say factor of my column that it's called outcome. All right? So in this case, I have an almost ready ggplot, but I also have to tell ggplot which visualization I want. And in this case, I want the histograms or the bars, and these are called geom bar. So we could run it like this. Let's do it. Let's see what happens. So in this case, factor, okay, you have the factor outcome. We will try again to do it without the factor to see the difference. But in this case, you have the 6 options from 1 to 6, which are the sides of the die, and the count, so the frequency on which this appears in my data frame. And you can see it goes from 0 to less than 200, so nobody reached the 200 mark, but it is quite even. So this is the discrete uniform distribution. So each side of the die has more or less the same probability of coming out of a throw, right? Because the dice is fair and each probability is the same of having a 1, a 2, a 3, up to a 6. So let's make this plot a bit better, because could be that later on we look at it and we don't remember anything, like what were we trying to plot here. So we put labels, labs, all right? And we want to say that we want to give it a title. So this is discrete uniform distribution, all right? And we want, maybe to give it a subtitle. You can type whatever you want in here, just it's for you to remember what this was for, right? And in here I will say 1,000 roles. And then I will give an X, a better X. I don't know, this factor outcome, it looks a bit weird and not so clear to me. So I can say this is the side of the die. And then I can give it a epsilon, which I will call, we can keep it count. We can say frequency. I will say frequency. Very nice. Now we have our plot with all the different, all the labels. And of course, each and one of us, of our plots will look a bit different. So mine looked at the most probable one was the 6, almost. Maybe in your plots would be something else, and like the bars will be a bit different. And that's because are just sampled randomly. All right, let me open Zoom to see if everything is okay so far. Questions about, and tell me if there's some things you didn't cover in the past few days, or if I'm going too fast or too slow, let me know. Drink a bit of coffee while. Good. All right, then we can move. We can move to the next.
Maybe give a thumbs up if everybody is okay with this.
Yeah, thank you. Rusty cough today.
If everyone is done with this code and, is ready to move on.
It
If you have
ran
it,
properly, no warnings,
yeah,
no errors.
like for me, like, I forgot the plus sign after the geom bar actually, and then my column, the X and the Y sides didn't get the labels, and I was wondering why, what was not happening, and then I realized I forgot one simple sign.
That's like, I feel like 95% of my error in R are typos or something like this. Very silly things but I'm always like, why? What is wrong with this code? I don't see it. Yes. Can we move a bit?
Yes,
Of course,
yes, of course.
absolutely.
Yes, yes. Is there something that you are
But
waiting or like you want to know anything here? Like, do you have any questions there? Like, which part was too fast? Maybe tell us that also.
yeah, no, that's completely
Okay,
fine.
sure. Okay.
Yeah, maybe also the typing. That's true. I'm always a bit typing fast, but yeah, please, I don't get offended. Tell me if you have to repeat it 10 times, repeat it 10 times. We're really moving in the at
Yeah.
your pace today. It's really important. That's what I want. Maybe while we just sit through all these new codes, maybe we can give it a try. I don't know. I had this in my head that the factor was better, but let's just try. I will copy this whole code and I will paste it down here and I will just try to remove the factor just to see what happens. Maybe nothing, but let's just try it. So to do that, so what I want to do, I can also remove the whole thing here, but better not because I always remove less or more parentheses. So I will just remove one parenthesis from this side and remove the factor. And I just want to run this again and see what happens. I don't know if you noticed, but I will show the two different plots. Nothing really big happened here. Like the bars are still there, right? They look a bit thinner and thicker, but that's not really the problem. Look at the x-axis. So this is the one with the factor, and this is the one without the factor. What has changed? That some numbers are shown in the when we have the factor. Maybe let's do this. Instead of the classic title, we say X is a factor here, and X is an integer here. You don't have to do it with me, but just pay attention to this difference. So in the plot where X is a factor, you can see that all the single digits are spelled out in the plot, right? While when it's an integer, only the even ones are spelled out. And this is because this happens when R treats the variables as numbers. Like I don't have to spell each number. You know that between 2 and 4 there is a 3, and between 4 and 6 there is a 5. I can just spell the even one, and that's enough. But if you treat it as a factor, R thinks, okay, each and every one of them is an important information, and it's a different than the other. And there's no correlation, link between them. It doesn't see them as number anymore. So this is probably just a visualization difference. It won't change your life, but it's something to keep in mind for the future. Because if tomorrow or the day after you do something in the code and you're like, but why? What is this? Sometimes it's like the tiniest thing. So this was just as an example what can happen when the data is in a different format. And I think you did this difference, right? In the one of the first days between a variable when it's a factor or when it's integer or etc. I'm assuming, but if you didn't, please let me know. But I think I saw it in the agenda for the past few days that you covered this. But again, if there's something unclear of what I'm saying, just please type in the chat. Right, so now we saw, if there's no questions, we can move now to the binomial distribution. So I will make a new comment, and I will call this one binomial distribution. Before I move forward, I wanted to also maybe have a look at how we can organize our R script so that it's a bit clearer for us. So if you go up on this side of the screen, I don't know if you can see my cursor. Can you see my cursor? I'm not super sure.
Yes, we can.
So if I click on this, show document outline, in this side, it will show when there's some headers. So I think you guys used Quarto in the past few days, and you could create headers for each section. You can do the same thing in the R script. There's different ways to do it. My favorite, you don't have to do the same, but my favorite is to just, on a comment like this, you have the hashtag at the beginning, and then you can type -4 times. Not 3, but 4 or more than 4. Minimum 4. What happened here, if you have a look at this outline on this side, is that it just creates a placeholder here for this section of my R script. If I do the same here, it appears another one. This is a great way to organize your R script because you can just jump from one to the other. If I click now on the binomial distribution, it will go down the script to where this header is, right? So this is just for you a way to organize it. Another way is to type for hashtags as well. So that's similar. It does this exact same thing. As you can see, there's no difference. So it's just a matter of preference. All right, questions so far? Can you guys confirm with me? You used Quarto this past few days, right? You did a Quarto session. Yes, good. So I also wanted to say today we will type together, and I will type and you will type in your computer. At the end of today, I will share Quarto documents file for you that have all this code all in one place. And so, yeah, if you miss something, you can always go back to this Quarto document. I will share it at the end of the day because I also put some exercises that there is the answer in those Quarto file, but we will do the exercises together today. So I don't want you to peek. So I will share them later on today. But yes, you will have all the scripts. All right, binomial distribution. Which one was it again? The one with two outcomes. So we could have example of binomial distributions. Give me some examples. What could be a binomial distribution? We do a tiny recap of what Kavitha said this morning. You start, Kavitha, one example, and then while they type the other ones. Flipping a coin.
Great. Yeah. Yes.
Perfect. So
Correct.
in a flipping a coin situation, we
Yes.
have
Yes.
two possible outcome, heads or tail. No, nothing in between and nothing more than that. So that's perfect. Another one could be success or fail, for example, in an exam. Another one could be presence or absence. That's something we as biologists, we do a lot sometimes when we go in a forest or something like that. We either record the presence of an animal or the absence. So it's always a 1 or 0 occurrence.
I see that you've typed, Shiva has typed conflict occurrence.
Conflict occurrence.
Can you explain a bit?
Can you explain? Yes, I never heard of it. Conflict,
Numbers.
but it could be also similar, right? A 0, 1.
A
Either it
0, 1.
occurs
Yeah.
or it doesn't. That's
Yeah.
interesting.
That's interesting. Yeah.
Let me put a note in my notes that I will Google it later. Conflict occurs. Maybe it's something related to your field. But
Which
yes,
field would this be? Any idea? Okay. It's binomial because it's discrete.
discrete.
Yeah. Conflict occurrence numbers.
I will make a
I need to Google this.
I will make a note. I will look it up. Yeah, super.
So anything that's 1 or 0, I think that's the main idea here. So you can
Exactly.
give a value of failure as 0, success as 1, and anything in any field can be a success or a failure.
Yeah, exactly. All right. But then since we like the flipping coin example, that was the first that came up, we can use the flipping coin. So to do that I wanted to write some examples, but we covered that. So to do that, the function in R for two possible outcomes is called R binom, which is in the stats package, which is also in base R. And if you start typing it, it's like stands for R binomial. So this would be easy to remember. If we start typing it, we can have this very helpful guide from SARA that says the binomial distribution, exactly what we are looking for. Density distribution function, there's a lot of different things, and random generation for the binomial distribution. What parameters does this function want? It wants an n, which, what would that be? N is like the one we saw before, right? So in this case, it's quite counterintuitive, but in this case, n is the number of time we want to repeat the experiment, okay? Okay, we go with it slowly. So n is how many times we want to repeat the experiment. Size here it's the flip of the coin, right? So we flip the coin of a size of x, and the probability will be 50% because it's always a binomial. So 0, yeah? Sorry?
Yeah,
Was
excuse
there?
me. It seems the view is frozen. I think you need to just stop and reshare it again.
Oh, of course.
Yeah, it seems.
Oh, give me a second. Where is the button? Here. All right, let's reshare.
Yes.
Desktop. Yeah, I can share the whole desktop or share. All right, let me try to type. Does
Yes.
everything works again? All
Yes.
right,
Yes. Now things are good. Thank you.
super, no problem. All right, so we said R binomial. So I just enter, and we need to give it this 3 numbers. Let's start with n. We keep things consistent, not to make things complicated, so we run it 10 times. And let's flip. How many coins do we want to flip? So the size is how many coins? We could be 1 coin 100 times, but let's make things a bit more interesting. We flip 10 coins 1,000 times. All right? You can also play with the numbers. Like it's not an exam, we are trying to learn how things work. So actually, maybe let's start simple. We flip 1 time, 1 coin. Yes?
Chichi, I think there's a question. What does size of X mean? So I think that's what you're
Yes.
explaining right now.
Yes, it's
The number of
counterintuitive.
time.
Yes. So n, before we add the size, right? That was the number of times we repeat the experiment. For R binom, that is n. So that's why it's important to know, and that's why sometimes it's even better to ask R what is what, right? We can also have a look at the help package. But so we flip. N is the number of times we flip the coin. All right? So we flip a coin 10 times. And size is how many coins are we flipping, right? So in this case, it's just me. I flip 1 coin at 10 times. All right? The probability prob in the binomial can be only 0.5, which is 50%. So I can either have 1 or 0, heads or tail, yes or no, success or fail. All right? So let's forget everything else. Let's try to run this code for now. If we run this, we have, like before, 10 times numbers that can only be 0 or 1. All right? So because I threw it 10 times and I threw only one coin. What happens if I increase this? It's 5 more times. So I flip the coin 15 times. What happens if I do this? There's only 5. All right? Is this clear? Like this, n is the number of times I flip the coin. I can go up to 1,000, like we did before, and that's what we're gonna do in a minute. But what happens if I change the size? There is now, what has changed? Wait, I have to open. I have to open the chat. I can't see you.
Maybe change the size to 5. I'm also curious about that.
Let's try.
Interesting. Why are there other numbers? The coin flip is just heads and tails, right? It should be 1 and 0. Why is there 2, 2, 3, 4 and stuff?
I want somebody to guess because it's not so intuitive, all right? So the first answer could be like, it's wrong because it should be only between 0 and 1, right? So this should always be 1. But that's not the case, right? Because the function is R binom. So it knows that it's only a binomial distribution. So why does it give us number that can go up to 4? And by the way, yes, it can go up to, let's put 10. What I don't understand. Just want you to like try to think about it. We can take 5 minutes thinking time. Yes, and 5, this is okay. I throw it 5 times, right?
Dr. Cecilia, I think we missed your last 30, 40 seconds because of internet unstable. So kindly repeat for it. Yes,
Of course. So let's do a cleanup because this is important.
Yes.
All right. So R binom, we saw already. Let's do it again. From this, it's for the binomial distribution. All right, it's only for that. So it knows that the outcomes can only be 0 or 1. We decide how many times we want to throw the coin, right? N is how many results you want R to give you. So we say n is equal 5. And then we go below, so I can put a comment and say that n is equal how many times, how many numbers, n of numbers you want R to give you. In this case, 5 numbers. All right? So we are telling R, okay, give me 5 numbers. Size, let's go back to this and let's put a comment. It's how many times you flip the coin for each of those results. You flip the coin for each number. So what happens here? For each, and then prob is the probability. This is, I think, the more clear thing among all of this. This is the probability. In this case is 50% chance because it's a coin, all right? So if I run, wait, let me close the outline here up. If I run this, what happens is that I want 5 numbers, and for each of this number, I flip the coin only once, all right? Because the size is 1. But let's say that for each of this number, I want to flip the coin 10 times, all right? So if you want to simulate flipping the coin 10 times, so in this example of this code, we flip the coin 10 times and we count how many heads, for example, we get for each n, okay? For each n equal 5. So this is for this code, all right? We flip the coin 10 times and we count how many heads we get for each throw, okay? So if I run this, we get a vector of 5 numbers, right? Each of these 5 numbers will be between 0 and 10. Why? Because it's the number of heads. So, for example, the first number, I threw 10 times, and 2 of these 10 times I had heads. In the second instance, the second experiment, I threw 10 times, and 4 times I had heads. The third time, the third experiment, again, I threw the coin 10 times, and I got back 4 times, only 4 times the heads. I need this to be crystal clear. So please, if I have to, I can repeat it once again, if it's not clear.
I think this is also very similar to the way I explained what a random variable is and what a random variable will be for a discrete or a binomial distribution, like a coin flip. So you are focusing on, like how Cecilia has said, the number of heads you get. So that's the reason you're only focusing on heads. It's not tails anymore. You're only looking at the ones you're getting, specifically in this case.
I will explain it one more, and while I explain it, I just put the comment, but please type in the chat, like, I'm lost completely, or this is somewhat clear,
Or easy, very easy, we move
super
on.
easy. It's not. I am also struggling sometimes with this. I'm like, wait, I need 0 and 1s. No, I don't. I need, yes, okay. Why does it show? Yes, let's do it again. So let's say it shows, let's use your numbers. Let's say it shows this. I copy it here, okay? This it could be a possible outcome, all right? So what this means is that the first 5, what does it mean? This one. It means that the scenario is that in the first experiment, or trial or however you want to call it. I threw the coin, I flipped, sorry, better. Flipped the coin 10 times, and 5 of those times the outcome was heads. All right? Let's take the four. Let's take the last one. In the last experiment, the last 7, this one, all right? In the last experiment, by the way, which was the fifth experiment, because the number of times I threw, the number of experiments I did was 5, right? In the last experiment, I flipped the coin. How many times? Always 10. Why? Because the size is 10. How many times you flip the coin? I flipped the coin 10 times, and 7 of those times, the outcome was heads. All right? I will put it in 2 rows so it's all visible.
So again, to go over it, you can only have 2 outcomes, the heads or the tails. And here you're assigning the value of 1 to heads, right?
Yes.
And if your size is, was that the first one? The first time that you did it, the very first time that you did it, that was just 1, right? Your n equals 1.
The first time, yeah. I can also run it again. Let's see. Let's say, wait.
The very first time,
I'm trying to run one that is,
but when your n, your n was...
n, yes. In this case, if I change it to 1, you mean?
Yeah. And it's, I don't see, just
it's
6.
only one number, and it's 6.
Yeah. So you're flipping a coin 10 times. Okay, so the n is 5 and the size is 1. I meant to say the size is 1.
Exactly. Another way to see n is like the number of experiments you're running, or the number of people, right? Because it could be, n could be like, if it's 2, let's say it's 2. It could be
flipping.
me and Kavitha. We are playing a game of flipping a coin. So let's also add or number of experiments. Me doing this experiment
versus
times. Or the number of people, let's say.
Yeah. So in this particular classroom, we are 21 of us, 21 participants on the Zoom call, right? So let's say 21 of us are flipping 10 coins. So it's not 1 coin, but 10 coins. So if 21 of us, of course, a coin has only 2 values, the head or the tail, so the 1 or the 0. But we also want to say at each flip, how many heads all of us are getting, the 21 of us are getting. And what is your value for this, Chechi?
Let's see. Let's run it. So let's say this is me. Chechi ran this experiment 10 times and she got 4 times heads.
Yeah.
Kavitha did the same and she got 6 times heads out of 10. Ajay did the same and he got 4 out of 10, etc., etc. So if we assign, these are 21 values, these are all of us, each one of us is a participant in an experiment, and we do the same experiment, and each one of us will have a different outcome, or maybe not, because again, the number of times we did this experiment is only 10, so it can be only between 0 and 10, right? The possible times we get a heads. All right?
Yeah. Okay. So they got
I
it.
will take a sip of water and I wait for the chat to confirm that we are good. But again, if not, no worries. It's quite confusing and it's normal for it to be confusing at the first time.
So
Maybe a
yeah.
thumbs up.
Yes, yes. So I think students are very, very happy so far.
Okay, good.
And yes, so let's take a break and get back at 12, around
Yes,
after 15 minutes, right?
15
Okay.
15
minutes.
minutes, yes.
Okay.
And then we
Makes a
start the
lot of
next session.
sense.
Sure.
Super.
Yes.
Okay.
Thank you.
Thanks.
We're ready? Super. Perfect. You can see my screen all right, I assume. And if you can't, just let me know. All right. So we left off with a very confusing concept. No, I'm joking. I hope this is clear. And if not, please let me know. But let's just say now that we want to plot this outcome. So we have our binomial sample, and so I will write a new one. So this I will keep as for explanation, but I will make a new one, which will be our binom. Once again, the n, since before we used 1,000, we will use 1,000 also in this example. All right? So we will get back 1,000 numbers from R, right? We will keep the size as 10. So let's say we are 10 participants flipping a coin 1,000 times each. And probability, of course, once again, it's a 50% chance because it's a coin flip. All of this, I don't want to print it in my R console because it will be super messy. So I will assign it a value, a name. So I will call it coin the results. Okay? Coin results. And if I run this, you will see once again here, coin result has 1,000 numbers and all of them are integers. All right? And all of these numbers are between 1 and 10 because once again, the size 10 means that there's 10 participants, or yes, let's keep it at participant. They all flip the coin 1,000 times and then we count how many times of the 10 they got heads. All right? As we did before, this is not a good way to plot. We need a data frame, right? As we saw earlier with the roll of the dice, we can't use this notation to make a ggplot. We need a tibble. So we can use exactly the same notation as before. And we will call it coin data. All right? To distinguish from coin results, otherwise it will overwrite. So coin data, we have again a table, and we need to name the column, right? Because this has no information of how we should name the column. So in this case, to make it even more clear that what we are counting is the heads, right? So each of this column, each of this number is how many times we got heads. So I think to make it super clear, we will name the column heads. You can also name it success or one or yes or yeah, anything that it's in a binomial, that it means that the success part. All right? In this case, it's a coin flip. We call it heads. Yes, heads equal. What do we want to put in here? We want to put coin results. All right? So we run this. It's the same code as before. And in fact, what you can see is that we have a data frame with 1,000 observation and one variable, meaning there's only one column. The column is called heads, and it has integers, numbers, 1,000 of them between 1 and 10. And this we know because the size was 10. All right? Now we can plot it. We do it as before, ggplot, open and close parentheses. We have to give it the data frame, which is coin data. And we have to give it the x and y axis of the plot. In this case, once again, we don't have a y-axis, or it's just the counts of how many times it happens, so we can just easily, the aesthetic of x is heads, the only column we have. All right? Remember the plus. And then, as before, we put the bar. So we will see something very similar of this. All right? So what happens? Let's run it like this. What will happen? As you remember before, I put the factor, right? I put heads as a factor, or in our case before it was the roll of the dice factor. But then let's say we want to, doesn't matter. The visualization won't change so much, but if you want, you can also do factor of heads. The outcome will be the same. Oops, I remember all your parentheses. And let's see, what will appear? I want you to visualize how the plot would look like before doing it, but let's run it. Was this what you expected it to be? For me, yes, because this was what we saw in the lecture before. This is the shape of, let's put it in the title, in the name, so we can remember. What was this again? It was all right, and this was 10,000 trials of 10 flips. 10 flips for each trial, all right? So what does this tells us? That it's more probable to have an even 50-50 distribution of our data. So if I flip a coin 10 times, it is more likely that I get 5 times heads and 5 times tails. It's really, really less likely that if I flip it 10 times, I get 10 heads. Same, if I flip it 10 times, it's very unlikely that I get 10 tails. So this is what this plot is telling us, all right? Are there questions? Oh, I just saw chat. Okay. Are there questions so far? This is exactly how we saw it in the lecture in the morning. We just made it with our own data. And of course, we can, let's say, 1,000 is not enough. We have to do it more times. If we do it again, and if we run it again, it won't change that much. Actually, we put it at 5,000, and it never happened in this simulation that there were 10 flips with 10 tails, because you see there's no data in this bar. but there is like maybe 1 or 2 or 10, very low chance of having also 10 heads. All right? But it's very common to have a split 50-50 chance. All right? So, if this is clear, let me know. Write in the chat, hand raise or anything. Otherwise, we can move to the normal distribution. I will make some space here. I don't see any, thumbs. Great. So I will move forward. But again, if you in a bit want to ask another question referring to the past things. Oh, coin data not found. What happened here? Could be a typo, could be that you didn't create this object. So once again, the coin results has the list of single items, so it's not a data frame. You have to create a new object, data frame, you can call it however you want. I called it coin data. You can call it anything else. And you have to give it typo. This also you can change however you want. I called it heads, and this is the column here. And you have to give it the list of numbers. All right? So what could have happened is that you didn't run this line, or there was a typo in this, or maybe you added here coin data because that's what I wrote. You called it only data, for example, because if I run this, call data, and this is.
It could be also if you don't the coin results, the variable, if you don't name the variable coin results,
Exactly.
because that's connected as well.
Yeah, exactly. So for example, now I cleaned everything. My environment doesn't know anything. So I run data and it says, coins result doesn't exist. And you can see that also here, it doesn't exist. So, okay, I run coin results, I run data, but then if I run this ggplot, it tells me not found because as you can see, I changed the name here and now it knows that it's called data, not coin data. So if I put it as coin data, suddenly R finds it. Did you find the error? Did it work now? Yeah, super. All right. Then let's move to normal distribution. Once again, I make a big title and I put my minus signs because then I can go back to my headers here. So, reminder, the normal distribution was the bell curve, which actually looks a bit similar to this one right now. So it's called normal because, as Kavitha said, it's like most of the time, most real life data re-enters into a normal distribution. That's why it's called normal. But that doesn't need to fool you because sometimes we have the assumption that normal is normal and then it's not. So always keep an eye. Anyway, in R, we will create our own data again, and the function for the normal distribution is called D norm. If you start typing it, once again, we can see what it wants us to give, and it wants the sorry, I was this wrong. So it wants the X, it wants the mean, and the standard deviation. All right? In this case, because I want to shake things up a bit, I want to do directly a ggplot. No, well, no. Let's do it simple. All right. Let's say that, okay, let's do the function first. We want the n, so x will be, oh, sorry, I'm so sorry. This is R norm. It's like the same as R binom. It's R norm, the function we need. All right, so let's retype, not d norm. D norm is something else. I got confused. R norm. All right, exactly. What you can see here, it wants n, which is again the number of times we want to run this experiment, the mean and the standard deviation. So let's say, because before we did an example with heights, right? We say we want to sample 1,000 fake humans, all right? And we assume the average height is in centimeters 170, because I'm in Germany and that's the average height here. And there are variations, of course, between this number. Not everybody is under 70. So the variation, the standard deviation from this number is 10. I will put this in 2 lines so you can see all of it. So let's go back to the function. We want to sample 1,000 fake humans, and we assume the average height, so the mean, is 170. And the standard deviation is 10. How do we write this function? We saw it before. This is just slightly different, but same as before. So n is equal to, in this case, this scenario with the fake humans, 1,000. The mean is 170. And the deviation from this mean, so we assume that the average is around 170, but how much it can variate between from this number, right? And we say that it's 10. Could be even higher, but with heights sometimes is a bit more strict. And let's say I am in Germany and the average is higher maybe than it is in India, and it's more like closer to that number. So the standard deviation is how much close to the average or to the mean is gonna be that number. So if I make a higher standard deviation, it can be further away from the mean, all right? So if we run this, we have a new type of numbers here. Let's save this as an object and we call it fake heights, so we can investigate it better. Do you see the difference here? Coin results was integer, so there were numbers with no decimal after. It could be only 0 and 1, and for any time we run this, a number between 1 and 10 for the heads. Same with rolls. When we had the rolls, it was an integer because it could only be 1 to 6 that were the sides of the dice. Fake heights, though, it's a discrete or continuous variable. You can see it from the output here. It's not defined numbers, right? It can take any possible number around 170 with a deviation of 10, right? So it's a continuous variable.
And
Yeah.
so, and again, here in your heights, I mean, it's also limited to the fourth decimal point. It could also be much longer. It can go, the numbers can go beyond what, like
Yeah.
these 4 digits after the decimal point. You've set it to 4 decimal points. That's also
Yes.
important.
I think that is standard in R. I would need to look it up. But yes, definitely. Yes. And you can see it because here in fake heights it says it's a number, not an integer. Num means that there will be, it's possible that there's decimal within. All right? So we can see again, these are too many numbers. I want to see only the first, I want to see the first 10 only. Oops. Head, not heads. You see, I make a lot of typo. It's not heads, it's head. I was thinking of the coin flip. So I want to see the first 10 digits, and as you can see, there's like a lot of different numbers that are all around 170, and that's the mean I chose. You can choose another number, like try to play with it. Okay, we want to plot it. Again, what do? We can't use this. We need to make a table. So, hides data. How do we do it? Table. We can also copy from here, but we won't call the column heads because this is height. And what do we put in this column that we called height? We will put this fake heights. All right? Perfect. We have our new data set, data frame, and we are ready to plot it. As you can see, when you see it in the environment, the decimal are gone. From here, it doesn't show you the decimal. So sometimes it's really important to see this notation here. If it's an integer, it doesn't have decimal number. If it's a number, num, it can have, even if it's not shown from this panel, all right? So important to remember. Let's plot it. ggplot. We want heights data. Once again, we give it the x. And in this cases, within heights data, it's called height. And we do a geom. Let's do a different one. Histogram this time. If we run it like this, as you can see, we have the distribution, the whole distribution of all the data we sampled of the 1,000 individuals. And as you can see, 170 falls exactly here in the middle. And overall, the shape is this bell curve that we saw some example before. In geomistogram, one value we can change is called bin width, which is how big are these bars, these histogram bars. For example, we can say 2, which I think is the default exactly, and nothing changes. But if we put it to 1, they will get smaller. And if we put it to 5, they will get way bigger. But the bigger the histogram, the more information you lose, right? Because the difference between a bandwidth of 5 and 1 is that you have more minute information within the same plot. And this was 2, which was, again, you lose a bit of information. And then, okay, if you put it at 10, you won't really be able to see that much anymore. All right? So this is a way, because Again, this is continuous variables, so you can play a bit with how the bins are, how big they are, but remember that it depends on which kind of data you have. If you have continuous variables like this with like a lot of decimal numbers, you might want to have a smaller bin width so you can see the information a bit better. All right, is everything clear for now? Yes. So I have for you guys a couple of exercises. We can do, I think I lost a bit track of time for this morning, but maybe we can do one or two and see how we do it. And yes, and I can also leave you the other exercises for later, or if we have some time at the end of the day, we can go back to it. So how I thought to do it is that I write you scenario and you will have to make sample and simulate your own data. What did we mean heads here in normal distribution? Heads, this one you mean? This line here?
I think
I
it's
think
meant to be like the header of the data. So that's what it's called, head. So that's just function as such to call the first
exactly.
10 values of from the variable called fake heights. So it's
Yes.
like the top, the header of that particular
Yes,
data
the
set.
top
It's not
10 values of the data frame. And that
Yeah.
is why, because if I run this, like if I run fake heights, if I print it, I see the whole of the data set, which might be a bit too much. And let's say I just want to check that the code ran well and the data is how it's supposed to be. So head tells R, okay, just give me of this data set just the first 10 values. And if I run this, as you can see, I have 8, 9, and 10, the first 10 values. I can also, so if I don't specify any number, it will give me the first 6. That's the default. So 1, 2, 3, 4, 5, and 6.
It's just a key to check if if that's that data that it's actually looking at. It's just a checkpoint rather.
Yes. Was that what you were referring to? Maybe if there was something else unclear, please let me know. Good. All right, I want to know, I will write here, because I think we have time only for one example, but I will write here, I want to know between uniform distribution, binomial distribution, and normal distribution. Please vote which example would you like to do, which exercise. So put an emoji on the one you would like to do an exercise on. And then we will do that together. And then I will give the exercise I will give you anyway. And then I'm here anytime if we have time later today or tomorrow to do it together. Otherwise, you can do it in the next few days and ask me questions if something is not clear. But yes, please vote. I give you 2 minutes.
Is it also clear if there is is it also clear that you understand the difference between the binomial distribution and then the normal distribution? Because both of them look extremely similar.
True.
Like it's like a bell curve for the normal distribution, of course, but for the binomial, it's not a bell curve, but it looks similar. But
True.
Is the difference clear?
Yeah, that's true. That's a good point.
Because for the binomial distribution, you're looking at success and failure. You're only
Mhm.
looking at zeros and ones. Whereas for the normal distribution, Yes, it's more relevant for us. That is true. And yeah, you're also looking at all different kinds of data, the average of the data, and the standard deviation of the data. You're looking at continuous data forms.
All right, then let's do a normal distribution example. I will type in the chat the scenario, and I will also type it in R, both, so you can have it both sides. I will give you 5 to 10 minutes, maybe 5, to do the exercise, and then I will do it so we can see if there's something unclear. All right? Perfect. So, I need to, oops. Give me a second. So, here it is in the chat, and I will also put it here. I will type exercise, and I will also read it out loud. So IQ numbers follow a normal distribution. The average is 100 and the standard deviation or spread is 15. Let's sample 1,000 humans. So you go back to your notes, type the code, and if you can, plot it, but for now, just use the function to create this sample size.
And
I
if
will,
you're also, if you want to share, you could also just share the little chunk of code, like just the little, without the plot and everything,
yes,
just what your variable is on the chat.
yes,
If you,
in few minutes.
yeah.
Okay, let me copy it and I put it in my screen and we can have a look. Super. Okay, we created this IQ score, which we used our norm. We sampled 1,000 humans. Perfect. The mean or the average is 100 and the standard deviation is 15. Perfect. We run this and we have our IQ scores. Once again, they are numbered with decimal. For ggplot, we need to put this in a tuple. I see here you left height, which is fine, it's just the column name. But I think in this case we want to call it, I don't know, IQ, the column name. Because let's see, if I run it, if I run it like this, we will have the IQ score data with the column height. It's a bit confusing if we look at the code again in the future. So let's call it IQ. You can leave it height, but for sake of learning, we will call it the column IQ. All right? And then in ggplot, IQ score data, and this we don't put the data from these values, but we will put the data from IQ score data, right? And in this case, the column is once again IQ. If I would have called the column height, I would have needed to put this as height. So this is the same column that it's here, which contains the IQ scores that we calculated here, but we need to give it the correct column name. All right, so we run this and we run the ggplot and beautiful bell curve. We used a bin width of 10. Good. We can also try to see how would it looked with a bin width of 2. And yeah, the shape is identical, it's just that I have a bit more information in there. All right. All good so far? So good? Did any of you have problems with this exercise? I see some thumbs up. if any question came up during this exercise, please let me know. I will leave this for a minute, but actually maybe let me also do this. I can paste it in the chat. Because every time you sample this number, it's always a bit different. So if I run it in my machine and you run it in your R machine, we will sample from random numbers different outcomes, right? And it will happen again if I run it again. So let me do this again. And if I plot it again, it will be a bit different than before. And this is because every time I run this code, R just starts again and randomly resamples all the 1,000 fake humans. And this is why it's also so interesting, because every time you run it, the curve is a bit different, but it's always a bell curve. Why? Because we are constrained by these two numbers. So the mean will always be around 100 and the spread will always be 15 points. So no matter how many times I run it and how many different shapes I have, it will always be a bell curve.
Yeah, but that again is with this specific data which is generated
Yeah.
using R here. So data is what we generate. And that is why the data that is generated in Cecilia's machine versus your machine is different. But usually if you want to plot a bell curve like this with your own data, then you should have entered your data as a data frame into R, and then you use your data frame and the mean and the standard deviation that you generate from your data frame, and then use the plot functions after that to see if it follows a bell curve. So that's the procedure, because we are not using specific data frames here. We're just using we're generating data and then looking at the plot. Yeah, so we're doing it at this instant it's generating.
Exactly. Yeah. Super. All right. I will stop sharing my screen, but please, if there's more question, let me know.
Yeah, maybe we can give another 2 minutes for any questions from the class. And if there are no more questions, how to interpret mean and standard deviation. Okay, so from your data in the graph, okay, maybe on R.
Let me share again.
Maybe share, yeah.
Yes, yes.
I think there are functions within R.
I'm sorry. Can you see my screen, right? Yes.
Yeah. So from this particular data, here you're saying what the mean and the standard deviation is. You're saying the mean is 100 and the standard deviation is 15 here from the 1,000 fake humans that you're generating. Like the mean IQ score is 100 is what you are saying. But in a normal scenario where you have your data from your 1,000 humans, like 1,000 actual real humans, you would have to calculate the mean. So for example, then there would be functions within R where you can use the mean function to find out what the mean of your data is. The standard deviation function can help you find out what the standard deviation of the data is. And then you use these things to put it in a plot and visualize your plot.
Yeah.
So to find out the mean and the standard deviation, I think the code is pretty straightforward. I think
we can do it with again. We can do it with this data. It's fake data, so it's hard because the answer would be the ones we put in. But in general, if you have your own data, so for example, let's do it with this IQ scores. We would ask mean is a function in base R, and we give the data frame. All right. Or actually, we can also keep the IQ scores.
Yeah.
So it's not exactly 100, but it's very close to 100. Yes, sorry, there was a hands up.
The student has a concern actually related to the Z score. If you are covering that, in the coming sessions, because there is a Z score, and then related to that, how to interpret the mean and standard deviation. And there are some exact Z score we divide into 99%, 60%, and 30%, the normal distribution. So I think the
Yeah.
question is related to that. Are we going to cover that in the coming session, like Z score in context of standard deviation and mean? So because there's some specific Z score related to the normal distribution probability numbers, no? So is it?
I'm not sure if we have a slide on this. I can't
No.
remember. So Z score, it's like how many standard deviations a specific point is away from the mean, right?
Yeah.
Yes. So, I mean, I think it's yes. So because in a normal distribution, I mean, the only thing I think is useful to know the Z score is like where a point sits, right, inside the bell curve.
Yeah.
And I think that's what our point was before with the probability of choosing a number. That was the like if I want a number between 80 and 110, how is my probability with this data set to fall within this range, right? And if you have a Z score of 2, for example, from one number, you know that scored higher than 97.5% of the population, because that's how of the bell curve. Maybe actually, Kavitha, can you? Oh no, I can also share the slide again. No, wait, can you share the
Okay.
slide again
Yeah,
of
I
the?
can. Yeah, I can. Close this.
Maybe just a minute and we see again the plot, and then we
Yes.
can see how to do that in R. Because I mean, it's a good question. Yeah, exactly. So usually you have this distribution of the curve, and you know that most of the data falls within this range, and exactly like this range that you see in yellow.
Yeah.
Right? And that is 97.5%. That's a fixed number. So 97.5% of the data always falls into the yellow range. Then there is the remaining is 2.5% sits outside of this range. All right. So as of what is the Z score, I think maybe you guys know already, but let's say it again. It tells you exactly where a point, like if you sample randomly from this yellow or this whole distribution, it tells you where exactly the point sits on the bell curve, right? If the Z is equal to 0, is within the average. And if it's 1 is 1 standard deviation above the mean. If it's 2 is 2 standard deviation above the mean. If it's -1 or -2 is 2 standard deviation below the mean, etc., etc. So it's like it shows you where the point is. To go back maybe to R, what we can do, I think there is a function. Oh wait, I will share my screen again, maybe.
Wait, I need to wait. Hold on. Let me stop sharing. Yeah.
Yes. Yes. I'm doing it live. It was not scripted, so the function should be scale, and you can put, for example, IQ scores. And you can see here Well, maybe let's give it a nice Z score. All right. And we see the first 5, okay? We said the first 6. How did I call that? Yes. So the first 5 numbers of the IQ score, the first one is minus 0.7 Z score, meaning is 0.7 standard deviation below the mean. The second one is 1.5 standard deviation above the mean. The third one is perfectly centered, almost, like if you ignore the rest of the number. It's 0.0. So the third number, I expect it to be 100 or very close to 100, all right? 0.2 is 0.2 points above the mean, etc., etc. So this is one way you can find the Z-score of your data. Does that answer the question?
Yes, it up to an extent. And actually, there are a few Z scores which are critical for the interpretation. As you correctly mentioned, no, like 99% data falls within this range, and then 30% data. So I think those numbers the student can refer with any book as well. That's not so important. But yes, you correctly explain, thank you for that.
No
Explain
problem.
the Z in the context of mean and standard deviation.
Yeah.
I think that answers the question perfectly. So thank you.
No, thank you, and please, yes, ask any time. The other thing I wanted to show, so one is the mean, and the other is SD as a standard deviation. So you can, in this case, once again, not so important because we set them ourselves. But if you have, like Kavitha said, if you have your own data and you don't know what is the mean and the standard deviation, these are the 2 functions you can use to find out. So this will give you the standard deviation, yes, around 15, that's expected, and the mean is around 100, as expected. All right?
And addition to this, it will be helpful if you can share few points. Why actually do we need Z score? Because I did not cover that. So if you just share
Yeah.
few thoughts, why actually do we need Z score?
Yes, it's a very important question. I think maybe we can have a look when we use real life data, but as a general rule of thumb, Z scores can really help to identify outliers. So in these simulations, wait, I stopped sharing my screen because then you can see me better. In this simulated data, it's like very fake data. We create our own mean and standard deviation, so there will not be any values that are extremely rare. If we go back to the heights or the weight, like Kavitha said, let's say that all adults in the world fall around, I don't know, 90, 100 kilograms of weight. Like if you are 30 plus of age and you are healthy, you will be between, I don't know, 70 and 80 kilos, 100 kilos. But there are some humans that weight 600 kilos. This is considered an outlier because it's not within the range we would expect, but it's also not within the range of the tail, like the very rare cases. This is outside, this is completely out of the ordinary. When you have this kind of data, real life data, it could happen that you have some individuals that are completely far off even the realm of possibilities, right? And that score can help you visualize which one of these numbers are complete outliers. For example, generally speaking, if you have a Z score of -3 or +3, that is considered an outlier. So you could maybe when you have your own data and you run the function to visualize the Z score, you have at a glimpse, you can see, okay, all my data falls between 0 and 2. Fine. If it is 3 already, there are outliers, which doesn't mean necessarily that something is wrong, but it means that you have to keep that in mind for your statistics and calculation, because outliers have the bad attitude of pulling every other point away. So we will see some examples later, I think tomorrow actually, that if you have some points here, let's say the weight, if we, as 20 people, we weight ourselves, we will be all within, I don't know, I'm just 60, 80, 90, doesn't matter. But maybe there is one, I am 150 and I'm so far away that then the mean gets pulled away from where the whole population is. So this is something just to keep in mind. Sometimes it's necessary and correct to remove the outliers when you know, okay, this was a mistake or this was an error in, I don't know, the balance or the we used to record the weight was broken and then it recorded a wrong number, then you know, okay, this number I have to remove. But some other times it's a real number and you have to take that into account. So going back to the Z score, I think I could be wrong. There could be more things, but what the first thing I can think about is to visualize and see if there's some outliers in your data. Confidence is same or different? I don't know if this is the right question at this moment. We will see confidence interval later, but yeah, this is also a good point. Sorry, Kavitha, did you want to say something?
No, continue. It's fine.
So confidence interval, we will see it later, but just briefly, when you have, for example, in this IQ scores, there are some ways to say, okay, I'm confident. I can assume that all the data is between this number, I don't know, 81 and 95. And this is the confidence intervals tells you where 95% of the data falls into, which again, it's very similar to this yellow range of the distribution. And statistically speaking, also when you write papers, when you say, this is my number, so I found out that the IQ score of this population was 98, and my confidence interval is between 95 and 100, meaning that all 95%, almost all, not all, of your data falls between that range, and the mean of that range is the number you said with confidence. All right, but yes, we will see that more in detail later. Any other? Oh, great.
Great.
Thank you for the feedback. But yes,